Hi everyone, this is Yukabuka and welcome to my home on YouTube. In this video, we will be looking at the file fs/char-dev.c, and this is the kernel source file that implements support for character devices. It does depend on a few other files from driver/base, and we may look into that if reading the source leads us there. But yeah, this is the file that we will be looking at and examining. Okay, so first things first, we see a bunch of includes. We see that there is a pointer here called cdevmap, and the type of that pointer is struct kobj_map. Now if you look at struct kobj_map, we can see that it has a very specific layout. It has a pointer to a mutex, or a pointer of type struct mutex, and it also has an array of pointers, and the number of pointers is 255. Each of those pointers points to an object of type struct probe, and within the struct probe you have things like a pointer to the next struct probe, so it's some sort of a linked list implementation. It has a dev_t dev, and I believe a dev_t is of type u32, but we can check that out. Dev t yes, so it's u long, so 32-bit unsigned value, right? There was we saw another one. What is that? Here we have kernel dev t, which also goes to an unsigned 32-bit. So that's fine, it's an unsigned 32-bit value. What else do we have inside probe? Let's see. We have an unsigned long range. I'm not sure what the range corresponds to, but I believe it's the number of character devices. But yeah, I'm hoping we will run into that as we explore the source, and it will give us a bit more of clarity on what this range value is. We can see that it's an unsigned long value as well, so it's a 4-byte unsigned value. And then there is a pointer to struct module. We do, when we write kernel drivers, we do set the owner to a value called this_module, and so I believe that that is what this field contains or represents. The next one is a kobj probe t star type. And what is kobj probe t? It's a struct kobj star of dev t int void star. Is that a function pointer? I don't quite know. No, this is not a function pointer. This is a slightly stranger syntax than I would have imagined. What is struct kobj star? Let's see. If it were a function pointer, I would have expected a different syntax, especially within the kernel. They use a different syntax for function pointers, but this star So this here is just a prototype. This, on the other hand, is a type def such that k-object probe t. I'm not too sure. I'm not too sure at all. I will need to look into this. Oh, we can do a quick search for what is obj probe t, but I don't expect to see any results immediately. Let's see. Okay, so someone's mentioned obj probe. Now you can see that each entry has a major and minor number for the device, and the device structure in the form of obj probe t, which is a kernel object which represents a cdev in this case. I see. Okay, so it's a kernel object that represents the device structure. Okay, interesting. Right. Bit strange. Anyway, so the next item that we have is a function pointer called lock, and the last one is a void star pointer called data. Okay, not all of the entries make sense, but hopefully as we read the code that will change. We also have a mutex defined, which is and initialized, and it's called char-device _ lock. Okay, so it's a lock that for all the character devices. I'm guessing if there is a list that maintains all the character devices, this lock is probably what restricts access to that list. Okay, so the next one is char-dev major hash size, and that's set to 255. And then we have a static char-devs array. So we have an array of pointers, and the array size is 255, where each of the pointers points to an object of type struct char-device struct. And this is some form of a linked list. As you can see that it has a next pointer, and then it has a major, a base minor, a minor CT. I'm not sure what that is. A name of size 64 bytes, and a pointer to a cdev. That is a pointer of type struct cdev star. Okay, interesting. And it has a will die comment. I'm not sure what that is about. Okay. So yes, that's it. However, we haven't looked at what a cdev structure is. Is that defined in the same file, or where is that defined? Let's jump to the definition. What? No, I think Source Insight is acting a bit weird. So let's have a look at this structure here. We see that cdev has embedded within itself a k-object struct, and if you're not familiar with k-object, I suggest that you look at my other set of videos which discusses the implementation of k-object within the kernel. It's a series of 6 videos. And then there is a pointer to struct module again. There is a pointer of type struct file operation star. Okay, that makes sense. And there is a list head list, which suggests that it is part of it is going to be part of a list. And there is a device number and a count. Also, it's interesting to see that there is an underscore underscore randomized layout. We discussed this in an earlier video. So what are the structures that we have encountered so far? We know that there is a global pointer called cdevmap. We haven't seen what it points to just yet. It's just a global pointer, and it's of type kobj underscore map star. Then we have an array of pointers and the array size is 255, and each of those points to an instance of a char-device struct. Okay, and that seems to contain details about every device. I'm not sure just yet. However, each of those instances has a pointer to a struct cdev instance, and cdev itself is a node in a different linked list. Okay, fair enough. So let's now go to the very bottom of the file to see what functions are exported, because I guess those would be decent entry points to start reading the code once we have looked at the global variables. Let's look at some of the initial functions. We see a register function, an alloc function, a cdev init function, and so on. And I wonder which function we should look at first. Is it the cdev init function or the register chr dev region function? So let's see. If we look at the source code for a driver that we have opened up here, does it call cdev underscore init? Yes, it does. However, is this function called before or after the char-dev region allocation? It is called after the char-dev region allocation. So we will look at this function first. Okay, let's look at this function. Okay, and what the comment says is that it registers a range of device numbers. Okay, from is the first in a desired range of device numbers. It must include the major number. It must include the major number. Okay. Count is the number of consecutive device numbers required, and name is the name of the device or the driver. Fair enough. So if you need devices 1 through 6, then you would pass in 1, 6, blah. So that's what you would do. However, let's see. From must be the major number. That is what they're saying. Okay, cool. So in cases, so you can call this function from the driver only in cases where you know what you want your major number to be. The major number is not in any way dynamically allocated or assigned. Okay, so within the function, what you have is you have a pointer cd of type char-device struct. Yes, so initially we had seen at the top of the file we had seen an array of size 255, which also had pointers to instances of char-device struct. Okay, the next variable here is called 2, which is from plus count. Okay, so that is one beyond the last device number you want to use. Then you have temporary dev numbers called n and next. Okay, again, it helps to remember that dev underscore t is an unsigned 32-bit value. And then we have a loop over here, and what the loop does is for n is equal to from, n is less than 2, n is equal to next, it iterates and performs a few actions. And if at any point it fails, it goes to this section here, and from n is equal to from n is less than 2, 2 has been made to n, that is the point up till which it succeeded. N is equal to from n is less than 2, you call unregistered character device region. Okay, so it's a form of cleaning up. If this function is asked to allocate from 1 through 6 and it succeeds all the way through till 3 but fails at 4, you do need to free the memory or the character device regions that have been allocated for 1 through 3, and that's what this loop does. Within each iteration of the loop, when it tries to register the character device region, what it does is next is mkdev of major of n plus 1, major of n plus 1 comma 0. Okay, so we can look into what that is. But if next is greater than 2, then next is set to 2. Okay, so next somehow tries to find a device number that is perhaps free, I don't know. But if that device number somehow gets to be bigger than 2, then you just set it to 2. Okay, and at that point what you do is you call cd, you set cd to the return value of __ register char-dev region. Okay, and into the register char-dev region function you pass major of n, minor of n, next minus n, and name. Okay, so if next were 2, then next minus n would be from plus 1, from plus 2, and so on. Right, so let's say that from was 1 and 2 was 6. So the total count would be 5. You would be calling __ register char-dev region with n is equal to 1, and next minus n would be 6 minus 1, 5. And for the next from is equal to 1, you would call it with n is equal to 2, you would call it with n is equal to 2, and next minus n is 4. Okay, let's look at the prototype for this function to see what that second last argument is. It is set to minor ct. What is that, minor count? I'm not too sure. Okay, let's see. But there is no early bailout from this function unless you have an error. Also, this function calls this loop calls this function count number of times, so it is a bit strange to call the background function register char-dev region as well, because let's see, yes, this is that. So the comment of register char-dev region says register a single major with a single minor range. Why is there a specified minor range? Something is unclear. Okay, let's take a look at the definition of the function. The arguments to this are major of n, minor of n, and so on. So major, base minor, minor count, and name. Okay, let's jump into this function. If major equals 0, this function will dynamically allocate a major and return its number. I see. Okay. So it is capable of doing that. Oh, okay, but it's not the expected behavior from register char-dev region, because it does not, I imagine, return. It returns a 0 upon success. It doesn't return the major number. So if you want a dynamically allocated major number, this is not the function to use. So in this case, let's see what it's doing. It has a pointer of type char-device struct, and you have a CD and a CP. Okay, you have a ret equals 0 and you have an int I. CD is an allocated structure of type char-device struct. Okay, and if CD is null, then you say there's no memory. That makes sense. Okay, sounds good. Okay, so the mutex that we saw earlier on in this video is being acquired, and let's take a quick look down there to see where it's unlocked. Okay, and it's only unlocked over here. Sounds good. And this demonstrates, are there any kmallocs within it though? I don't want to jump the gun. We'll keep an eye out for it. Yeah. So what's happening here? If the major number is 0, then you call find dynamic major. Okay, and so on. But in this case, this function is called only if we know what this major number is, so we won't dive into that just yet. This if block will not be executed. How about this one? If major is greater than or equal to char-dev major max, then I think this is 255. Oh, that's 512. Then you print out an error message saying that the major number is invalid. Okay, so the maximum possible major number seems to be 512. Fair enough. What happens next? Next, the allocated structure over here is being assigned values. So CD arrow major, CD arrow base minor, CD arrow minor count, and all such values are being assigned to CD. The name is also being copied here. Okay, sounds good. This is a strlcpy. Okay, fair enough. The next thing that is done is I is equal to major to index of major. Okay, so it takes some major number and returns an index of some sort. Okay, let's look at this function because it's crucial to our understanding. Okay, so there are two definitions. One is for block devices and the other is for character devices, and all it does is it does a major mod char dev major hash size. Okay, and if I remember that, it's let's see, this value is 255. Okay, so that's because this array here is of size major hash size and it's 255, so it's essentially just a mod. It's just doing it a mod on the major number and making sure it's within the acceptable size. Fair enough, because a major number can go all the way up to 512 while the size of char-devs is only 255. Okay, so what happens next is you take the pointer CP and then you set it to char-devs arrow I. Okay, makes sense. You have star CP, CP is equal to ampersand CP. Okay, so you're just iterating through the list pointed to by the char-dev at char-devs of I. Okay, and you check if the major number, if the major number is greater than the major number of the device we are trying to register, or if the major number is the same as the device we are trying to register, and the base minor is greater than or equal to the base minor that we supplied, or if the base minor plus the minor count is greater than base minor. Okay. Yeah, it seems... Is this a sanity check though? I'm not too sure. It does a break at that point, and the comment says that it's checking for overlapping minor ranges. Okay. It finds the old minor, it finds the old maximum, it finds the new minimum and the new maximum, and it checks if there is an overlap of some sort. And if there is an overlap, then it returns an EBZ and then goes to out for cleanup. At which point the newly allocated CD structure is k-freed. However, if there is no overlap, then CD arrow next is star CP and star CP is CD. Okay, so it's just inserting the new CD into the linked list. Okay, I'll just go through this check here once more because I'm not too clear on what's going on, and that's the only missing piece here. So there is a linked list from the CD pointed to by char-device of I. Or ampersand char-device of I. So as you iterate each of those items of type char-device struct, it's checking if there is a char-device struct whose major number is greater than our major number, or let's see, I am trying to figure out what the precedence is. It's not immediately obvious to me. So this is one case right here, or it's checking if this and this. Okay, so that is a case of its own, and this is a whole case of its own, right? So if the major number that we have provided is greater than the major number that we are currently looking at, then we just break over there. Or if the major number is the same, but if the major number is the same and if the minor number is greater than that of the base minor that we just provided. So if the major number is the same but the minor number is greater than or equal to base minor, if it is greater than or equal to base minor, or so what is this case here? That is, this is a given and then it's either this or this. One of those needs to be true. So if the base minor is greater than or equal to the base minor that we provided. Okay. Or if the base minor plus the minor count is greater than base minor. Okay, so I guess what they're checking is our base minor of a lower range than what's already been allocated. For example, if a base minor of say 4 to 8 has been allocated, its base minor would be 4 and the minor count would be again 4. Or let's take a clearer example, 4 to 9, such that the base number of such as the CP arrow base minor would be a 4 and a CP arrow minor count would be a 5, right? Now if we pass in a minor number of say 2, the base minor is greater than or equal to base minor, because 2 is less than 4, and base minor plus minor count, that is 9, is greater than base minor. Okay, if that's the case, it will just stop iterating. If, however, what happens if, I guess the next is, okay, so it's a KZ alloc, which means the next pointer is initialized to null. So the last element on this list will always be null, which means if it cannot break out, then then after iteration, then it will just point to the last element, right? So that's what it's doing. Because there may be a case where you have a base minor of 4, a minor count of 5, but the base minor that we provide be say 11, right? In that case, neither of these two OR conditions will succeed, right? So at which point it must be inserted at the end of the list. Okay, so it seems like this implementation tries to make sure that no two devices or no two device registrations happen such that there is an overlap of minor numbers, given that they have the same major number. That's effectively what's happening. Okay, that makes sense. Cool. So at this point, I guess it unlocks the lock and it returns. That makes sense. And we've looked at the rest of the function, so yeah, it looks good. The next function we will be looking at is alloc chr-dev region. Let's take a quick look at that and see if it's a long function, we shall look at it in the next video. If not, okay, this seems to make sense. Let's have a look at it. The alloc char-dev region, the comment says that it registers a range of character device numbers. The dev is the output parameter for the first assigned number, yes. So when you use alloc char-dev region, it means that you don't have a specific major number in mind and that you can use whatever the kernel provides you with. And as a result, as you can see here, the device number is passed by reference. It's not passed by value. So in alloc char-dev region, you have a pointer of type struct char-dev device struct *cd, and you are effectively calling the same function but with the major number of 0, a base minor, a count, and a name. So it's effectively the same internal mechanism. The only difference is that a major number of 0 is passed so that it will try to allocate a major number. And once it returns the value, it takes CD major and CD base minor and it calls mkdev on that. Mkdev is a macro that right shifts the major number a certain number of bits and ORs it with the minor number. Okay, that makes sense. There are two versions of mkdev. I'm not sure which one will be taken, but I will assume for now that it is the one shown here. So minor bits seems to be 20 bits. Okay, so you left shift a 32-bit value 20 bits and then OR it with the minor number. That's what it's doing. Sounds good. out of curiosity, the major number is an unsigned it. It's a 32-bit value. Okay, that makes sense. Sounds good. And you set it to star dev so that it's returned back into this function, and you know what the major number is. You know what the device number is, right? You don't get just the major number, you get the major number or the base minor number, or with the base minor number. Okay. The major number left shift a certain number of bits, or with the base minor number. Okay, that sounds good. So in this case, when they do major, it's effectively going to be right shifting that a certain number of bits to get the major number. That's what it's going to do. There are also a couple of things we need to jump into. We need to look at this if block to see how it's finding the major number when major is 0. And how it does that is by calling a function called find dynamic major. Let's take a look at that. What find dynamic major does is it has an integer I and a struct char-device struct star cd. Okay, and what it does is it starts from the last element of char-devs. Char-devs being this array of size 255 which has pointers to instances of char-device struct. It starts from the last element and it goes all the way till 234. So starting from the last element, it would be index 254. It goes all the way till 234. So 235 to be exact, so about 20 or so. And if any of those pointers are null, then it just returns that. Okay, so from the end, if any of those are null, it just returns that value. However, if none of those are null, it won't return. And so there is something else going on here. We see that this value here is called the char-dev major dynamic end. Okay, and at this point we have char-dev major dynamic extended start. Okay, and that starts at 511 and the end is 384. Okay, so it is beyond the bounds of char-dev, right? But we do know that those major major numbers are can be allocated up to 512. So as a result, from 512 to 384, we have a loop, a decrementing loop. Why is it 384? I'm not too sure. I would sort of have expected it to go all the way down to 255, but I'm not too sure why it's done this way. Okay, in any case, it goes from 511 to 384. Okay. Yeah. It's actually 383 because it's I greater than, yeah. And within that, it takes a CD as char-dev's major to index of I. Okay, and CD is equal to CD arrow next. Right. Now what is going on here? So effectively, this outer loop is taking major numbers one by one, right? So eventually what this function needs to return is a major number that can be used. And this attempt failed, so it's trying out other ranges of major numbers it can use. So in this loop, it's going from 511, I think, to 383. It's taking each of those major numbers and checking if it's a possible candidate for use. After that, it's doing a major to index. We did see this earlier. I believe we did see this. Yeah, it does a mod 255, right? So it does a major to index on that character device and gets a pointer and stores it into CD. Okay? And it iterates that list which is pointed to by CD arrow next. Yes, that makes sense. Okay. And if the major number at that point is equal to I, it means it's already been used, right? Because that is how we inserted it based on the register char-dev region. Yes. So if that major number is already used, you just break. However, if the CD is null, or if the CD arrow major is not equals I, then you return I. If CD, so that is only after you break from this, right? Yes, so there is a check. If it is already null, you won't go inside this. Okay, makes sense. So if cdef equals null, or if cdef arrow major is not equal to I. Well, if you did break out from this loop, that means that CD arrow major is not equal to I, right? Yeah. I'm not sure why there is a check for CD arrow major not equals I. I mean, if it is not null and it goes inside, then the yeah, it would break, but it's not a continue, it's a break, right? So if it is equal to I, it will break and it will execute this line. So that's why there is a check. Okay, that makes sense. Maybe a way to implement this better, I don't know, would be to replace this break with a continue and replace this clause entirely. Would that work? If CD arrow major is equal to I, then that means it's been taken, so you just continue. And if it's a null, then it means that, yeah, maybe that would work. I'm not sure. In any case, now we know how the major numbers are calculated dynamically. In short, we have a check to see if at the end of the char-dev's array there is a null pointer, and if so, that major number is just assigned. If not, you go from 511 to all the way to 383 and then check if the index pointed to by major of index of that I value has the major number set in the linked list corresponding to that item, and if not, you just return the I value. Makes sense. If at the end of it all there is no way to get a major number, then it returns ebusy. That sounds great. Alright, cool. So in this video we have looked at how register char-dev region and alloc char-dev region work internally. Contrary to how the name sounds, it doesn't really allocate any memory region of any sort, similar to a VMA or anything of that sort. It just allocates a major and a minor number and then creates some structures of type char device struct, right? The cdevs have not been initialized as far as I can see. they're just set to null because it's allocated using kzalloc. And we will probably see more about cdevs as we dive into other functions. That's it for this video. I hope you've enjoyed it. If you've enjoyed seeing me struggle reading code, then hit like and subscribe. I will be uploading more videos on more of the functions that are shown in this driver here. Bye bye.